So good to have everybody here tonight. Dan Howard, the director of the STEM Academy here at Foster Ridge High School. First, I wanted to give a shout out to all of our STEM Academy students who are here tonight. So if you are a sophomore student, would you stand up and do a quick shout out? I've got a lot of my sophomores. And then my seniors who are here, who can't wait to graduate soon. All right. And juniors from last semester, one thing I love about the STEM Academy is because it's kind of a multi-year program, just seeing everybody throughout the years and the support that we get from our seniors and our sophomores to help with these kinds of things, and vice versa. So thanks everybody for being here. And of course, we can't forget our current juniors, so let's give them a big round of applause right now for the hard work they've done this semester. So guys, the STEM Academy, as many of you already know, it's a multi-year program. And my goal in the STEM Academy, or what I'd like to see, is students develop essential skills that we're going to use for the rest of their lives. So things like critical thinking, like problem solving, effective communication skills, and teamwork. Those things we develop kind of as we work through projects and all kinds of things like that. Of course, we're also here to develop a lot of those skills in engineering and biotechnology to help students get to that next level. And a lot of students, when they come in as sophomores, have limited engineering skills. Some of them have never even coded anything before, and it's kind of scary to get on a computer and start coding from scratch. They haven't CAD'd or 3D printed manufactured things, haven't done any long-term labs like that. And so this progression that we take of building up skills, both those soft skills and the engineering type skills, it's a journey, right? All of it's a journey. And I feel so privileged to be a part of this, because after these projects are done, I start to see towards the end of the semester all of that stuff coming together. So all of this learning that was done in previous years and other classes in the STEM Academy to make these projects come to life. And I love seeing the teamwork and the communication all coming together, because really those are the skills that are going to be used for the rest of their lives. And I know that that's not the part they like about the class, but it's important. So juniors, I want to tell you the experience that you guys have been through over the last, whatever it's been, 3.5 months. It will benefit you. I had the opportunity to visit multiple college engineering programs over this last year, and my wife gets irritated with me because I stop at every booth and I ask lots of questions about their projects they're doing and all kinds of stuff. And she's like, can you go now? But it's kind of fun to geek out on that stuff. And one theme that I heard from a lot of people as I talked to them about our program is they said it's really beneficial. It helps students that have gone through a big capstone project like this to prepare them for the college setting. So juniors, I don't know where you're at in terms of how you feel that things ended this semester, but I promise you that this will benefit you as you move on to the next level. So thanks everyone again for being here tonight. Without a lot of support, these projects would not be possible. So I wanted to take a minute to thank some of our supporters. First of all, our STEM Advisory Board. And I think I have a few advisory board members here. If you're on the STEM Advisory Board, could you stand up real quick? Andrew, I don't know if some people know. That's great. I didn't get a chance to say that. So thank you guys so much. The STEM Advisory Board, they serve multiple purposes. They kind of are in the background for a lot of what we do, advising us on how do we prepare curriculum so that these students are ready to move on to the next level. And so I asked them about what should we be doing here so that they're ready. And then many of them serve as mentors. Deep has been a mentor on multiple projects that included coding and electronics, and Andrew has helped with many projects, in particular students who have gone out and done some lessons with younger kids in their projects. So I really appreciate all of their support. You can see that they're made up of a lot of people from CSU and some other people in the community at different organizations. So again, if you could give them a round of applause, I'd appreciate it. all of these projects, most of them go beyond my skill set. So I get to help out when I can here and there. But I ask all of the teams at the beginning of our projects to find a mentor, somebody who knows a lot more than I do that can guide them on the project. This is a really important part of the projects. And so we reach out and find as many teams and mentors as possible. And so if you mentored a team this semester, if you would stand up real quick, we'd like to give you a round of applause. Casey works, is it infectious diseases? Is that okay? Microbiology stuff at CSU, again, way beyond what I normally do. Chuck's helped on a few of our Gokart projects with the electronics. And Mr. Brittingham is one of our students who knows a lot, was able to help out too. So did I miss anybody up there? So thank you guys. Our mentors really provide that boost when the students run into problems. They help them move forward. By the way, just a quick check with you guys. Juniors who just finished your projects, how many of you, raise your hands if you ran into any issues, like difficulties on your project? Yeah, all of you should be raising your hands, right? Because everybody ran into problems. And so that's where our mentors come in. I try to step in and help when I can. But really, I just want to emphasize too that when you go through that process of failing and getting back up and the persistence of trying again and going back to the drawing board, that is a super essential skill. So sometimes those failures are what we need to help us learn and grow in our knowledge base. So thanks to everyone who was able to support us. And the last group that I would like to thank is the people who provide supplies and financial support for us. So we reach out every project, every team is asked to get some kind of financial donation or material donation. In this semester, Penrose, Tap House and Eatery held a fundraiser for us, and the Market Skate Shop got us some supplies for a project, and King Soopers consistently gives some monetary donation. Otter Cares, I just want to highlight Lucy from Otter Cares and the partnership that we have with them. They have consistently for the last few years, the Otter Cares Foundation has supported us financially. But they go beyond that, and Lucy actually comes in and allows the teams to pitch their projects. And that's just been a huge benefit, I think, because it's a real life skill of, hey, we need money, here's what we're going to do you like what we're doing? And so the students prepare a presentation, come in and give a live pitch to Lucy and sometimes some of the other staff. So a big round of applause for all of our supporters, especially. Lastly, I want to thank everybody who's helped out to set up tonight and running the booth and the tables for food and everything. So thanks all of you guys for helping out. It's a huge help. I always like to have one of our seniors come up and just give a little pep talk to those of you guys who are about to present. So I'd like to invite Alan McFarland up to give you guys a little encouragement before you speak. And then we'll start on the part you guys are here for, which is the presentations.
I'm Alan. So STEM students here are learning a whole bunch of detailed skills in a specific area. So I did a video game project in Rust, by the way. It's the future of programming for any of you who are still wondering what the future of programming is. It's Rust. And from this project, I was able to gain very valuable technical skills in the specific domain that I intend to pursue in the future. In the same way, the Maglev project has learned extremely complicated physics and extremely complicated mechanical and electrical engineering, because many of the people on that group are intending to go into mechanical and electrical engineering fields as well as physics. So by gaining these practical skills in STEM here, they are gaining a good intuition which will help them in classes. So they will have a higher leg up as they proceed in their future. So to all the STEM groups here who are doing mechanical engineering, who are doing welding, know that you have learned a great deal which will be very useful to you in your future endeavors.
So I'm going to go ahead and have our first team that's going to be presenting. That one's not as good, maybe, because this one's not as loud. We have had a different venue every time for this for the last 3 presentations, and so every time we're learning the new technology for the place we're at. Gokart team, you guys ready to come up? All right, so our first team that's going to be presenting is our electric go-kart team, and I'm going to pass the mic off to them. Feel free, if you're thirsty or hungry, to grab some more snacks. We got plenty back there.
Hey guys, thank you for coming in. We're the STEM Electric Go-Kart team, and we'd like to present our project to you we've worked on this semester. Alright, so I'm Cameron Kick, and I'm the team leader and manufacturing.
I'm Lucas Hisrich, and I handle the communications and manufacturing part.
My name is Felipe Sampaio. I was in charge of the design and also helped out with the manufacturing.
And I'm Eli, and I worked on assembly and manufacturing of the cart.
Well, our project was to convert a previously used go-kart that was hybrid into an electric go-kart. So, yeah, the go-kart was donated to us by an old amusement park, and we decided to make it electric and make it efficient.
So why did we choose this project? Well, we chose this project because carbon dioxide emissions have been growing rapidly recently, and we wanted to prove that electric cars are more efficient and that they're safer and more reliable than gas cars. So we approached this project as if it was a scaled down cart, building our principles around this to accomplish multiple goals. And as you can see on the graphic here, with the gas car, you can see that only 16 to 25% of the energy that goes into the car is actually being transferred to the road, compared to the electric car, where you can see 87 to 91% is actually being transferred. So it's way more efficient and better for the environment.
So before we could actually start building the go-kart, we had to establish some primary goals that we wanted to achieve. So the first goal that we wanted to achieve was obviously to create a functioning electric go-kart. But our team also wanted to make sure that it went at least 20 miles an hour. To do this, we had to replace the engine as well as remove old unnecessary parts. And throughout the whole process, one of our main goals was also to ensure that we're safe while working on the go-kart and while driving it. And then our final goal was that we wanted to create a platform for future STEM students to use and build off of.
All right, and to just kind of complement the primary goals we had, we just kind of developed some secondary goals that could also kind of improve the quality and functionality of the cart. So we started with just removing the excess weight, that kind of just so we could get as much speed as possible. And then we added this cool Alcantara racing steering wheel, just for like the aesthetic of it. And then an easy way to adjust the tension and alignment of the motor so we could have it easier for the future STEM groups. And also just increase the runtime.
This flowchart is a visual representation of our process throughout the manufacturing of the go-kart. Everything just flows into one another.
So just a brief overview of the timeline. So our first stage was project planning, but after that, we found a mentor, established our goals, and established our team roles and responsibilities, as well as inspecting the cart and seeing what needed to be done. And so that led us into phase 1, where we did research and planning, and we had multiple new components that we had to order in, such as the engine. And we were on a budget, so we had to find the right engine that was also a bang for our buck. And then after that, we ordered those components, which leads us into phase 2. In phase 2, we CAD'd a lot of components, which, for those of you who don't know what CAD is, it's computer-aided design. And then after we CAD'd it, we would transport the files to the plasma cutter and then plasma cut out those components. And then in addition to that, the components that we ordered, we replaced the old components with those. Which leads us into phase 3, where we made adjustments and then we tested the go-kart.
So just one of the first things we put into action was this fundraiser that we had at Penrose. We went to DC Oaks and asked them, but they referred us to Penrose. We had 10% of all the profits that they made on that night would go to the STEM program. And we are proud to announce that we raised $270 for the program. And yeah, you guys can clap for that. Yeah, we also made this cool flyer that we put around the school and handed to some teachers who wanted it.
Alright, so this is the phase 1 of our project. And as you can see, in the winter when we first went out and saw the cart, it was in pretty rough shape. It had been left uncovered for most of the winter. So our first plan of action was actually to buy a tent that we could put on it, which unfortunately made it broke. But as you can see, when we were inspecting the old components, you can see that the old engine was broken, which is actually on our table over there. It was broken by the previous project, so we had to order a new engine for it. And then we also saw that this steering was not very ergonomic, so we decided to order a new steering wheel, as Lucas mentioned, to improve the functionality and aesthetic of the cart. And then we also overheard from the previous project that the runtime of the cart was not very long. It was about 15 minutes, so we decided to add another battery that we found laying around to improve the runtime of the cart.
Our phase 2 of our project was the manufacturing and assembly. So as I was talking about, or as my group was talking about previously, we designed a new adapter for our steering wheel as it wouldn't fit previously. And also we designed a new new mounting plate so that we'd be able to move our motor, make sure the tension was right, make sure the placement and everything was good. So yeah, as you can see, we designed new parts to be on shape. As you can see, that's the mounting motor and installing the new components, and also there's the manufacturing process as after we plasma cut it.
So prior to the project, our group had pretty much no knowledge of fuses and how to wire the engine. Or the motor, my bad. So Chuck came in, shout out to Chuck, he saved our life with this project. And he brought us a bag of goodies of fuses, fuse housing, wiring, and everything that we needed to get all the wiring hooked up. So, yeah, thank you to Chuck again. And then that picture to the far right was our steering wheel adapter. I don't know if you can entirely see it, but the bolts didn't fit. It was too big of a radius, I guess. So, yeah.
Yeah, and so the phase 3, kind of the final phase, which was really like these last 3-4 weeks, was just testing and seeing what motor mounts and configurations were the best for making it run. We had to go out there on the road and we'd make it go, but maybe the chain would jump or fall off, and then we'd have to kind of go back to the drawing boards. That's kind of how it all goes together. But it was really just trial and error, and we ended up, which what kind of motivated us to make a adjustable plate, so then we wouldn't have to go through all this trouble of getting the perfect one and just re-drilling holes and all that. So, yeah.
So throughout this project, we encountered a lot of challenges. Pretty much every day, we'd find something that would cause us to go back to the previous step and rework something or rethink something to make it work. So it tested our resilience as a group. We'll fix this. As you can see, our tent broke. Thankfully, after most of the snow was gone, but yeah, big snowstorm. And we also had this issue with the plate, as you can see here. Before this one was very thin, the torque of the motor would pull the plate down, which actually bent the plate. So when we tried to run it, the chain would fall off, and it was damaging our components. So thank you to Mr. Denauer, we were able to design this new plate that we were able to move sideways to adjust the alignment of the chain and forward and backwards to adjust the tension. So, but yeah, that was a big issue for us. We also have the sprocket down here, which is hiding behind the wheel. We had to drill new holes because they did not fit with the flange that we had on there, which is what it drills into. So we had to rework a lot of that and drill a bunch of new holes to try to get this right, or else the chain would jump and bounce and fall off. We also had a lot of issues with the wiring, but thanks to Chuck, we were able to get that figured out pretty quickly. But yeah, basically it's been a journey with the car, but thankfully it works in the end.
As we only had limited time, around 3 months or 1 semester to do this project, we would, if we had more time, we would decide to replace the brake rotors as they are bent from previous groups' use and like just how old the go-kart is. We would bleed the brakes as they have been sitting for a very long time. We would remove some of the excess weight, as well as we would like to implement a reverse feature and also add regenerative braking to the go-kart. And another thing, as you can see, we would like to apply a fresh coat of paint to the go-kart.
So I want to give a big thank you to our mentors. So thank you so much to Chuck. You helped us with the wiring and the fuse, and without you, we definitely could not have gotten the go-kart to run. Thank you to Brian Trejo at CSU, who coordinated us with the CSU go-kart team. And thank you to the CSU go-kart team for helping us figure out what battery configuration would best meet our goals. And thank you to Mr. Bedin for helping us weld, plasma cut, and just general assistance in the shop. And then obviously, thank you so much, Dana Howard, because you helped us so much.
No jumps on the stage. I usually call this the Franken cart, like Frankenstein cart, because this is the third project team that's like done something with this. And Chuck's history goes back to the beginning because his son was the team lead, I think, right, on the original go-kart that they got donated from a cart place down in Boulder. They pulled it out of some warehouse, it wasn't working, so that team converted it to electric. Last semester, a team converted it to a hybrid, and now it's back to electric. So we'll see where the future of the Franken cart goes. Next up is our electric skateboard team, right? You want to pull that one up for us, guys? Yeah, all right. So come on up.
We are the electric skateboard team. I'm Evan, I'm the project manager.
I'm Merrick, and I'm the utility communications guy.
I'm Jackson, I'm the design coordinator.
And I'm Trevor, I was in charge of photography and research. So our project was obviously to create an electric skateboard, but with our electric skateboard, we wanted to limit our CO2 emissions and create a more efficient design for our skateboard.
The impact, a lot like the go-kart team here, we were aiming to limit CO2 emissions. And a fun fact,
since 1990, 60% of CO2 emissions have risen. And electric skateboards, they kind of serve as an eco-friendly substitute for cars.
So some of our main project goals were to make an electric skateboard that was both rideable and works. And we also wanted to be safe and reliable for the rider. And towards the end of the project, we wanted to test some of the max speeds and how long it runs for, basically.
So this slide is our overall timeline. We broke it up into 4 different sections: the research section, the design section, the creation section, and the assemble section. So first, for research, we had to research background information, components, different parts, and finally make sure that all of them were compatible so that we wouldn't waste our money and we wouldn't waste our time when they finally came in. Once we got all of our parts in, we moved into the design section and we laid all of our parts out. Spent about a week on this, just made sure that they would all fit together, kind of saw how they would fit on the board, and then made a plan for how we would move forward. For the creation section, Evan spent a lot of time programming, and me, Jackson, and Trevor went down to the shop and built our gear, built our mount, basically all of the parts that we would attach to the go-kart. And then for the assembly section, this just started about 2 weeks ago, and we just started attaching everything to the board. We welded our mount on there. We screwed in the other part of our mount that connects to the motor. We put our gear onto the wheel, and we put everything in the box that holds all the components together.
The design, as you can see from this outline here, everything kind of works together. The board helps support the motor, and also the mount also connects that together. And then the motor is attached to the bell in the gear, which is also attached to the board, so everything kind of works together. And then, as you can see, our design criteria, we want to be very durable, so that means using strong parts so that after a few runs it won't just break. Also, high performance, we needed a motor that was strong enough to move the wheels, even with like having a person that's like 100 plus pounds on it. And then lastly, safety and reliability, using predictable and consistent parts so that there's no like hiccups and potential like damages. Here's our creation timeline, and our first step was obviously parts, finding parts that are going to work and be compatible with each other, but also be quality and not worry about it breaking. So our second step was programming, and this took a little bit. We had to figure out which program to use, which was called VSC Tool, and it was just kind of a new program. I had never programmed with it before, and we had to learn about that. And then for our third step was the mount and the gear, and so we had to create and design our mounts and our gears separately. So for the mount, we had to find aluminum so that it's going to be sturdy and stable enough to actually carry the person on the board. And for our gear, we had to CAD it and design it on shape, then print it using a TPU filament that was going to be stronger and more reliable. And then for our assembly, which was the final step, was just putting everything together and testing it and making sure that it all would work.
So these are just some of the pictures we wanted to show you from our project. And on the far left there, you have a picture of some of us soldering some of the components. Right there looks to be the VSC and the receiver. In the middle, we have one of us working in the shop building the motor mount that connects the motor and the board. And on the far right is what all the electronic components look like when they're outside of the box, which they're encased in.
Moving on to our budget, the majority of our budget was spent on our electronic components, our motor, our ESC, and our remote. We didn't have to spend very much money on our materials. We're lucky enough to have a nice wood shop outside that had most of our metal and wood for us. The only materials that we had to purchase were some extra skateboard parts. Most of it was donated to us by the market. And then we needed to purchase some wires to build our loop key so we could safely turn on and off the board. And then 25% of it went to miscellaneous stuff. We had to purchase 2 different belts that attached to the gear and the motor. And then we needed some XT60 and XT90 connectors also to build that loop key.
And here are some of the specs of our motor and battery. On the left is our motor there. It's a DC brushless motor that has a max power of 5,500 watts. Then on the right we have a lithium-ion battery that powers the whole thing with a max voltage of 42 volts and a working voltage of 36. Its average lifespan is about 15 to 20 kilometers. Yeah.
Challenges. Our team experienced a bunch of challenges, especially with the equipment. Our boot key failed several times, so just having to recreate that, that was a problem. And also finding material that is like strong enough for our board and also like not too big, not too small. And another challenge was our remote broke like just 2 weeks ago, so that was a big step back. And also with our programming, the DESC tool software was very hard to use, so Evan had some struggles with that. And yeah.
And so what we would do with more time. The first thing we would do with more time is obviously test our electric skateboard, find the top speed that it can go to, the battery efficiency, and the battery lifespan, and just kind of compare it with other modes of transportation like a car or an electric bike. And then what else we do is we mess around with the design a little bit. We create more aerodynamic designs for our battery case, our gear, and our mount, just kind of see how much, how well our electric skateboard could be built. And then we'd also just play around with the different board shapes and board sizes. Like if we had more time, we would experiment with a shorter board or a longer board just to see the differences, and also experience with bearings and trucks and all that.
For the key concepts and procedures that we learned, as Dan Howard mentioned, critical thinking was important for us. We experienced a lot of challenges, and the ability to kind of think outside the box and move forward became big for us. Being able to divide and conquer. At the beginning of the project, the four of us spent a lot of time together researching and designing, but as we moved into the creation phase, we split up so that we could maximize our time and get our project done. So that became big for us. And then finally, the most important thing is we learned how to ask for help. We came in with very limited knowledge on our project, all the electronics and all that. So asking our mentor, Mr. Bevan, down in the wood shop to help us with that, and of course Mr. Dan Howard became big for us so that we could overcome those challenges and move forward.
Some of the things that we learned that we take home from this project is we learned how to persevere when our remote broke. This little plastic piece inside of the remote that we can't fix broke, and we learned that we can still use the board without it. And when we were making our gears, just not having 7 prototypes of it not working. We also learned that how important planning is, like why we're doing something, what we're doing, and when we're doing it, and having that communicated through the whole team is very important. Then we also learned on some hands-on skills like soldering or coding like Evan did, or even like working out on the tools in the shop.
Lastly, a very big thank you to the Falls Ridge High School Wood and Metal Shop, Market Skate Shop, Mr. Bevan, our mentor, and also Mr. Dan Howard.
I tell the students at the beginning of all these projects, whatever you think is going to take you a day is going to take you a week. And I remember watching these guys sitting at the soldering iron for like 5 days straight, and the next week I'm like, you guys are still soldering, right? And then something breaks and we're re-soldering. It's a constant battle, especially when you're working with limited resources. So good job, guys. All right, let's see. What's our next team up? I don't remember the order now. You guys have it pulled up for us? Okay. Our mechanical hand, you guys know. Just come up here and get me off stage.
Test. Okay. Hello, everybody. Thank you for coming. Our project was building a mechanical hand. My name is Benjamin Santangelo. I was the lead designer on the glove and the lead construction.
My name is Amber Thorland, and I was the lead on Arduino and the lead on code. Hi. Sorry. Hi, I'm Melody, and I was the lead on CAD and PCB. So, why a mechanical hand? For First of all, we thought that it would be a great project to dip our feet into the world of engineering, as it had many components, including CAD, Arduino, and code. And also skills that we didn't anticipate learning at the very beginning, including like soldering or like PCB design. And though our project right now is very preliminary, we hope that in the future we can contribute to technology to assist in environments unsuitable for humans, and also to explore options in remotely working traditionally in-person jobs, including examples like remote surgery. So this is a diagram Melody created, and it showcases the 4 main components of our project, which are the mechanical hand, the breadboard, the Arduino, and the glove. Essentially, our project takes flex sensor values from a glove and runs those through code, which turns them into numbers that correspond to servo speed. The numbers that show the servo speed move the motors at that specific speed, which winds the strings and moves the hand.
Primary goals. As previously mentioned, we did not actually come into this project with a lot of experience. A lot of it was sort of immediate, like teach ourselves how to do it. Arduino and code, if any of you have ever done it, is incredibly complicated, but thanks to the amazing perseverance of these 2 individuals, we were able to learn quite a bit. CADing was also another very challenging thing. It's very easy to trace actually how good you've gotten at CADing. Like, it just requires you seeing your designs move forward. And Melanie and I learned quite a bit. Efficient wiring. Wiring is an incredibly important part of virtually every engineering project, and to do it well is a struggle because you don't want it too simple or too complicated, but most of all you just want it to work. And then actually putting everything together, you could have every individual component work on its own, but getting it all to work together is a real skill that we learned quite a bit about. Alright, so our project timeline involved roughly a week of research and design, figuring out actually how we needed to do this. Arduino and code lasted virtually the entire time because we needed to constantly learn and figure out what we were doing. All of our putting it together, PCB soldering, and sort of final assembly was these last few weeks. Gosh, what is it? It's troubleshooting. There are a lot of issues with virtually everything, and troubleshooting, like, you're never done with it. There's always something you can do. So that's why that little line goes beyond, because it's never done. And then this last week was us putting together the poster back there and this presentation up here.
So this is the breakdown of our budget. We estimated to spend about $370, which includes Arduinos, PCB, flex sensors, and servo motors, and of course other miscellaneous costs such as solder and duct tape. Alright, so the first component of our project is CAD design, which is like the 3D printing. And we first had to figure out which software we wanted to use, and our options at that time was SolidWorks and Onshape. And as we've said many times, we came in with like barely anything. So we decided to use Onshape just to be able to get something on the screen.
I'm going to talk a little bit about all of the designs. This one over here, it's a TPU, it's a flexible filament. It returns to its original shape after being bent. We originally went with this because it was going to require less work and we didn't have to come up with a solution for the fingers to retract. Eventually we scrapped that because it was really complicated and very finicky. We then moved to a more anatomically correct model, 3 segments of finger based on hinges, shown up at the top right, and then our palms, which, as I mentioned, you can trace your CADing skills, very basic to much more complex. So yeah. No, wrong way. Work.
Okay, this is the final design for our project. As you can see up in the top corner, we have 3 segments and 3 joints that are obviously anatomically correct. And then we have our palm down here. So one of our challenges actually was trying to figure out how to attach the finger to the palm. As for some reason we didn't think to use like just like a joint as any of the other fingers that we made as we built, and we tried to make something like really complicated. So next time we'll reference our hand and try to make something that's accurate. And to explain the rest of our project, as you can see, the string in the front, that's the string that runs from the top of the finger down through the hole to the motor, and that provides the main mechanical movement that's going to move the fingers. And then the elastic in the back, if you can see from the lights, is the force that retracts the finger back.
Okay, so in the first couple of weeks of our project, we had to do a lot of research, and one of the biggest decisions that came with that was deciding what coding language to use. We were between Python and Arduino, and they both have their benefits and challenges. They're both pretty easy to learn. We ended up going with Arduino because we used it in our STEM survey class, so I had a little bit of previous knowledge. But despite that, I still knew virtually nothing, so I started with LEDs, buttons, single servo motors, flex sensors and servo motors, and then ended up building my way up to multiple at a time. And I also learned like complex topics, but also very small topics, such as the fact that resistances, they actually do matter, and I can't just use the prettiest colors. So.
To sort of talk about the glove, up here, if you can see what the pointer is, I don't know how well you can see it with the light, but these sort of like orange and segmented things are flex sensors. Those are the things that are actually measuring the degree of movement of what your fingers are doing. And then there's a lot of wires sending that information to our Arduino.
So the picture on your guys' left. Oh yeah, so this picture, it showcases pretty much the first time we put everything together. So we have the organized wires, the glove, the PCB, kind of just everything put together. So that's it was an exciting moment in our project because we kind of got to see things come together and actually do the thing. And on the other side is a picture of the code, which basically just shows how we map our flex sensor values into servo speed, which creates our project.
Alright, so this is PCB, which is our printed circuit board. And first of all, we had to pick the software again, obviously. We were picking between KiCad and EasyEDA. And we had no knowledge coming into this, actually. We didn't even know that we were going to build this. So under recommendation from Ryan, we decided to use EasyEDA. And as you can see from our design, these big boxes right here, those are the JST connectors that we soldered onto the custom PCB board that we got back, which are the white things up there. And then we got surface resistors, actually, instead of through-hole resistors, and they were the hardest thing to solder on. I'm not gonna lie. We spent like a week trying to solder on those surface resistors. So honestly, lesson learned. Next time, use through-hole resistors instead of surface resistors.
All right, this is the very first photo of when we actually put the code and the mechanical hand together. It is very rough, demonstrated by the copious amounts of duct tape on the right. That is a big help, by the way. Society is held together by duct tape. But it actually worked for a little bit until we broke a few things, but this is sort of the first time it all came together.
Actually, this is the first time it came together, where we put
We have progress.
So this is the first time our hand actually came together, and we put one finger on there. It was actually the only other day that I missed. So this is the exact video that Ben and Amber sent me after school.
We have progress.
So these are graphs that show the flex sensor values being mapped to the servo speed. So the top graph shows the flex sensor, so those are being read by our haptic hand, and they're sent through the code, which creates that second graph, which shows the servo speed. So they correspond to each other, which is kind of cool. That just represents that. Okay, now we're going to talk about our challenges. So one of the biggest challenges for me was finding external power sources because, I was trying to just connect it directly to a central power strip, and that would cause me to short circuit my computer multiple times, more than I want to admit. So that was definitely a big issue, and actually in the past couple of days we figured out how to fix that issue, so we had to rewire the whole thing. But definitely good because I don't short circuit my computer anymore.
We didn't really have a formal mentor. We sort of had two like half formal ones. Again, we'd like to shout out Ryan and Connor. You'll meet him later, but he was a monumental help as well with Ryan, and just actually getting this project to work when we hit those roadblocks. And yeah.
Alright, so another problem of ours was mobility. And something that we didn't realize until later was that the 3D prints really weren't that smooth, so we had to do copious amounts of sanding, like with like sandpaper. And it actually helped a lot. And it helped a lot with power too, so that it wasn't catching on things.
One of our first goals of the project was to make our haptic hand, or our mechanical hand, mimic our haptic hand exactly. And we didn't know this at the time, but we went with continuous servo motors, which is probably a bad idea. With the continuous servo motors, it was very hard without additional sensors to get them to mimic the exact movement. So looking back, we should have used 180 degrees servo motors, which would let us code to the servo degree as opposed to the servo speed.
The copious amounts of duct tape explain this part, but it's sort of a last-minute throw together. We had originally planned on creating a more specific motor housing compartment, but due to time constraints, we weren't able to do so. So if we had more time, we'd make it less haphazard.
And organization, which is like all the wires that you saw in all the photos, and they're really time consuming because we had to take apart our project like a lot. So we had Amber put them back together wire by wire, so thank you, Amber. And honestly, shout out to our soldering skills, because honestly that helped a lot towards the end.
Looking forward, we're probably going to take this project in two directions. I'm most likely going to head up one idea. They're going to go on their own. But I plan on potentially over the summer taking this and making it a lot more specific, doing the actual mimicry aspect, and potentially adding more than just the fingers. Maybe adding a wrist, going further, and making it actually grip something.
And Melody and I are planning on taking on more of an educational pathway. We're planning on simplifying the project and probably adding a couple other simple components and hoping to teach that to younger generations of students in our local community. And our main purpose with that is to kind of just get younger students excited about STEM like we are. So share our passion.
Yeah, so if you wanted to contact us about making this possible, please let us know. Thank you so much.
As mentioned, OtterBox does a lot for us. Pretty much all of our funding was covered by Otter Cares for this project. They gave us $375, and we only spent around $370 of it. So big shout out to them. Yeah, they did a lot for us. Thank you. Also, we'd like to shout out Fossil Ridge in general. This is an incredibly unique environment. Always helped by Mr. Danaher. He's a really great teacher, creating a really unique environment. Thank you to the STEM Advisory Board for making this happen. And thank you, Ryan and Connor. Once again, you were monumental, and we couldn't have done this without you. Thank you all so much. Have a nice night.
I remember vividly sitting, I was helping another team and I just kept glancing over at Amber's table with this huge mess of wires and going, I hope she doesn't ask for help. Because you can imagine jumping into something like that and just when she says, do you know why this isn't working? And I say, no, I don't. So I just want to applaud your team for the divide and conquer technique. You guys did a great job of splitting up the workload, and the amount of learning that you did to accomplish the things you did was spectacular. So nice job. All right, and I'd like to invite our research team on the antibiotic properties of honey, who is missing one team member today. So
Okay, so we're the antibacterial properties of honey group.
My name's Allie, clearly very sick, but I'm the team manager. our team leader and photographer. And our other teammate, Lucy, wasn't able to make it tonight, but she was our team communicator. And I'm Hannah, and I was the team treasurer. So why did we choose to do this project? Antibiotics are common tools to treat different illnesses within hospitals. However, when overused, bacteria can become antibiotic resistant. So we wanted to test a natural antibiotic. We chose honey and see its effectiveness compared to normal antibiotics that you would use in a hospital. We used 4 different types of honey to see which ones demonstrated the best antibiotic properties. So our goals within this project, our primary goals were to successfully grow bacteria. We also wanted to test at least 4 different types of honey, and after that we wanted to compare the effectiveness of each type of honey. Our secondary goals were to compare the results of our honey with the results of antibiotic to get a baseline for those results. We also wanted to test different concentrations of honey to find the minimum inhibitory concentration, which is the minimum concentration needed to begin stopping the growth of the bacteria. We also wanted to maintain a sterile field and learn basic microbiology techniques. So our project design. After we did some research, our first step was making agar and nutrient broth, which were the 2 mediums we used to grow bacteria in our project. We also learned how to use an autoclave, which is a machine used to sterilize both agar and nutrient broth. After that, we worked on inoculating our bacteria, which was putting the bacteria in the nutrient broth wells or on the agar plates and growing it so we could test if the honey inhibited the growth. We also worked on propagating our bacteria because the bacteria will begin to die in a very short period of time, up to 3 days. And so we had to propagate it at least once a week, if not twice, in order to make sure that those bacteria colonies were staying alive and we could continue our project. We also worked on incubating our bacteria and just making sure that it would grow consistently. Finally, we worked on pipetting our 4 different types of honey onto those bacteria plates to see if they would inhibit growth. So starting on the left, we have some images of our project, and that's going to be us inoculating our staph bacteria onto blood agar plates, and we also inoculated E. coli onto regular agar plates. The next picture over is a picture of us inoculating the bacteria into the nutrient broth wells. And after that, there's an image of our agar slants, which we use to propagate our bacteria and keep it alive. And the final picture over on the right is an image of our agar plate after we had inoculated the bacteria and pipetted 4 drops of honey onto it. So the total cost of our project was $38, and as you can see, the bacteria was the most costly part of our project, and then the rest of it was spent on honey. So the results of our project. We found that buckwheat honey was the only honey that consistently inhibited the growth of bacteria. We found that its minimum inhibitory concentration was 80%, so at an 80% dilution, it would start preventing the growth of the bacteria. We also learned that the buckwheat honey inhibited growth of both E. coli and staph. However, it worked better on E. coli. And after some research, we found that buckwheat honey was better at inhibiting the growth of bacteria because it had a higher sugar content, more minerals, proteins, and total phenols than other types of honeys. All the other honeys that we tested did not consistently inhibit the growth of bacteria. This is a graph showing some of the results that we received. On the bottom, you'll see the different types of honey we had, and on the side, that's going to be the different concentrations of honey that we tested. The red line going through our graph is going to show the transparency of the bacteria. So the more transparent the bacteria was, that means the less colonies that grew, which means that the honey inhibited some of the growth. And as you can see, buckwheat honey was the only honey that successfully inhibited the growth of the bacteria, starting at 80% dilution. And then, with some extra time, we used blood agar plates provided for us by our generous mentor, and we were able to find that the strain of sap we were using was hemolytic. And this just means that it breaks down red blood cells faster than other strains of that bacteria, which also means that it is pathogenic. And on our pictures, you can see the colonies of the staph as the white dots on the plates. So what went well and what didn't? We faced many successes and challenges during this project. Some of those successes were we were able to successfully compare the results of our honey to the results of actual antibiotics. We used ampicillin, and this gave us a baseline for our results to see how effective the honey actually was in inhibiting growth. We also worked to ensure consistent results for our buckwheat honey. So after we realized that buckwheat honey was one of the only honeys that inhibited the growth of bacteria, we did multiple trials with multiple different dilutions to see which one was in fact the minimum inhibitory concentration. And finally, we worked to maintain a sterile working environment with the autoclave, gloves, goggles, and different sterilizing techniques. And some challenges we faced were not being able to count the individual colonies. This was a problem in the beginning of our project because not being able to count the individual colonies meant that we weren't able to get quantitative research or results as easily. And we also had bacteria growth in our petri dishes in the beginning that was unrelated to our inoculation of E. coli and staph, but we correlated this with our incubator and realized that if we just sterilized it and cleaned it out, then that would make our results more consistent. And finally, our project was very time consuming. Anytime we'd autoclave our materials, we'd have to wait a day for that process to be over. And then we'd pour our agar, and we'd have to wait a day for it to dry before we could inoculate our bacteria, and then we'd have to wait a day for it to grow before we could actually gather our results. And if we had more time, we would have liked to test more types of honey, including Mucuna honey, which is a medical grade honey. We also would have liked to test more different types of bacteria, especially because staph has been known to be more antibiotic resistant than other bacteria. Finally, we'd like to give a thank you to people who helped make this project possible, including Mr. Danahauer, Ms. Keeter, Professor Grease, the STEM Advisory Board, and the FRHS Science Department.
Thanks, guys. Good job. We'll have our Propulsion group come up here. And I just wanted to say, while they're coming up, I wanted to just give a shout out to Casey. There you are. He invited the girls on the team to come into his lab, where they do a lot higher level research than we're doing here. But it was really generous to have the girls come in and learn some techniques from, there was an undergrad student and a PhD student, I think. And so they kind of showed them some techniques, and they donated some supplies to the project and whatnot. And that's just one of the many ways that CSU partners with us in lots of ways, allowing students to come in and see like what does the next level look like, what could we be doing in the future. It's really cool. So thank you a lot for having us all, and I enjoyed it. So, okay, we'll the Propulsion team, come on up. So where do you see on the Propulsion team?
Oh, you want me to? So yeah, I'm Grayson, and I was a team lead, and I did a lot of the CAD designing. I'm Lauren Burton. I was the electrical expert, the one who wired the actual thing, and I also wrote and
refactored all the code we used.
Hi, I'm Kai. I did all of the documentation, finances managing, and most of the basic research that was done in this project. So our initial research, we decided to research a Japanese train system called the Shinkansen, basically because it is a far, far more advanced version of what we were trying to do with our project. We researched and tested Hall effect sensors to figure out if we could incorporate that into our project, as well as MOSFETs, and we researched what capacitors we would use for our project and how to wire them in parallel.
So we initially decided to do this project because electric vehicles are becoming more and more prevalent in our modern society and more necessary to avoid a lot of economic issues as well as the global pollution crisis that we are dealing with. And
so our plan was to create a electromagnetic propelled train system. Well, I guess more just a train. And our goal was to have it go 30 miles an hour at least, which is definitely possible because it was supposed to go up to a maximum of 45. You can see these next two are secondary. As those we see on the project, these are basically, it's hilarious. I'll tell you why. Yeah, so those are secondary goals that we weren't quite able to do with this block.
So our original design cycle through a bunch of different possible ideas that we could do. We settled on an idea using just capacitors wired in parallel and solenoids to help actually propel the magnet forwards. We ended up reducing the solenoid amount in our final project due to time constraints and other electrical issues, and we decided to remove our original Hall effect sensor idea because nothing we really did worked with those, and we'll explain that pretty soon.
So the initial creation process, our first step was actually designing and brainstorming how we would tackle this issue. But as soon as we got those first designs down, we had incorporated MOSFETs, which are a special kind of transistor that basically allow electricity to flow once you apply voltage to one of the pins. We used solenoids, and those are just basically copper wire wrapped in circles to create a magnetic field. And the capacitors, which store electricity and are capable of releasing that electricity significantly faster than a battery could. The last section of design we did was the actual physical track, and we created a shell for the magnets because the magnet, one, could not slide super smooth in the first tracks we used, and two, it got broken very easily after, well, doing pretty much anything with it.
So, project anyways, so shipping delays, as you know, it took a really long time to get our capacitors running, which unfortunately took the first 2 weeks. So we weren't able to test this fast. Breadboard resistance. We couldn't use breadboard. We have capacitors, and that basically is way too hot for it to handle. And even if it doesn't melt, it would just not work entirely. And I think probably the biggest is the issue with MOSFETs. It melts. It's a one-time use only. So that's pretty good. And probably, yeah, so that themselves is pretty, those were problems in the clinic. Right, able to fix them. Well, sorry. We're able to fix the MOSFET problem, but it requires.
So for our finished project, we were able to successfully fire the capacitors and get the magnet to launch forward. However, we don't, one, have it recorded, and two, it fried almost all of our MOSFETs. we successfully did it, but we had to fully replace all the MOSFETs that we used, which was a pain to rewire. And yeah, we would have liked to increase the speed of the launcher, and we would have liked to create a much longer track, as our current track is extremely short.
So a few of the key lessons we learned was how to wire these capacitors in parallel, which it sounds simple, but it's kind of scary having a power supply that large near your body. We had struggled a lot to incorporate the Hall effect sensors, but we eventually got them working and then phased them out of the design entirely. But we know how to use them now. We had learned how to make all of the pieces that we needed. So we had created the rails, the little magnet casings, and then we also learned to actually use pretty much every part that we had found in one of those little demonstration and learning kits for an Arduino. And we also learned to order things sooner than 2 days before you need it.
Unfortunately, our original data is going to see when you increase the pairs of solenoids, how much faster or farther we can go. Unfortunately, because it only fired once, we weren't able to get that. So, unfortunately, we don't have the graph. I would love to give you guys that, but we just don't. But we actually did some testing on the number of turns on solenoid. Each turn actually increases the actual magnet strength, which is really interesting. Up to something. I think it was about 18. Yeah, 50 total turns around. So yeah. But yeah, I use that.
So for our project budget, we spent exactly $253.96, split up into various random costs. We bought about 12 MOSFETs, just in case we accidentally fried them, which we did. We bought 2 spools of copper wire. We bought a bunch of capacitors. We bought some sensors, some screws, some magnets, and resistors that we needed to actually make the voltage work, which it didn't originally.
We would like to give some special thanks to a couple of people, mainly Mr. Danahauer for running this whole STEM project, providing a wonderful classroom for us to learn at our own pace and learn things that we actually have interest in. We would also like to thank Otter Cares for providing us the money to actually do this project. Even though we didn't completely get it working, we learned a lot. It works once. Okay, it works once. It works. We got it to work once, and unfortunately we cannot show you here that it works, but take our word for it. Thank you for helping fund this project and letting us attempt to accomplish such a lofty dream.
And also thank you to Connor Peach for helping us out on multiple occasions with some of the basic wiring, as without him, we would have probably failed even more.
No joke, last Tuesday we had like absolutely nothing working. He is such a legend.
And thank all of you for coming here tonight. We genuinely appreciate it. And we appreciate the support that the STEM group gets. Thank you.
I heard once that the bulk of a long-term project all happens in the last week. I think for these guys it was the last like 48 hours. No. Grayson, how long did you say you worked in the last few years?
82 hours.
82 hours. Okay. We were even in here on Sunday trying to get some stuff working, so props to you guys for pulling things together, because I know you spent a lot of time on that, especially more recently. All right, our last project presenting, last but certainly not least, is going to talk to you about their special snow shovel project. So come on up, fellas. Hi.
Hello everyone, we are the Self-Propelled Snow Shovel team. I am Stephen Hebert, I am the team lead of the project. I did all the CAD designing for this project as well as helped with the manufacturing of the shop.
I'm Connor Dietrich. I was the programming and electrical lead, so I did all of the wiring and programming for the project.
Cooper Sipperly, I'm the shop and assembly technician. I welded everything.
Alright, let's get started. So the reason for our project is we wanted to make a snow shovel that would make clearing snow easier, especially for people who struggle with that, such as elderly people. Alright, so our why. Shoveling is hard when people struggle with it. We wanted to make a shovel that's easy to use and accessible to anyone. We wanted to make it super efficient, super powerful, and also very reliable. Alright, so some goals of the project is we wanted to focus on power, so making it comparable to other products such as snowblowers. We wanted to make it cheaper than other products, as well as more efficient, quieter, more powerful, and also more tangible and easy to use.
So here's our project timeline. We started back in early January with our research and CAD phase, where we began researching what we actually needed to do to accomplish our goal, along with our initial CADing. About a month later, in early to mid-February, we began obtaining parts to start manufacturing our stuff, getting our electronics and starting the assembly of all that. And then late February, we moved on to manufacturing with our 1/8" steel, along with actually getting all of our electronics ready to go. And then mid-March, we moved on to our final assembly phase, where we began testing everything and creating that. So here's our initial research on things like our motors, gearboxes, battery, miscellaneous electronics, our metal, all the important things that we actually really needed to use to get this project done. I'll give you a second to look over that.
Alright, so this is kind of a look at the design phase. So the first model of this project involved using one direct drive motor attached directly to the wheels. We later opted to use 2 smaller motors with gearboxes that would then attach to the wheels using gears. And our final project uses sprockets that attach the motors to the wheels.
So on to electrical development, the big thing. So we initially were planning on using standard Arduino-compatible motor controllers, but we soon realized that didn't fit our needs and pivoted to using Talon SRX motor controllers provided by Robotics, thank you, which actually delivered the power that we required. You can see all of that there. We then put everything together, or everything that we had at the time, and made sure that it all worked. Once we made sure that everything worked, we moved on to adding a second motor and a second Talon SRX. We then upgraded to a beefier Arduino and a lithium iron phosphate battery so that we could actually make everything self-contained and move on with our project. And that's when we shifted focuses to start focusing on our final wiring harness, along with refining our user interface and how you would actually control the shovel. That's when we actually implemented our LCD screen, along with implementing potentiometers to control motor speed, LCD contrast, while the LCD screen provided essential data while we would actually run it. Finally, we assembled everything into our big thing. Once we confirmed that everything was working, well, there it is, you can see all of it up there. But once we assembled our entire circuit, we made sure everything was working flawlessly. We put it into our project, and that marked a big milestone in our project's development.
Okay, so starting off with Stephen's CAD, we figured out that we needed 16 square feet of steel which we soon got and started plasma cutting. And then while we were doing that, I was learning how to weld. And along with assembling the housing, we were creating the shafts, the sprockets, the tires, and also the bearings, which we tried to press fit in, but they don't press fit in, so we welded them. I wouldn't do that. And now that we're sort of making the housing and sort of finishing that up, so we got the main blade mounted and everything welded together, along with the nice shiny lid attached with very modern minimalist hinges. And the final total assembly was a whole team effort. So while Connor added the electronics, me and Steven integrated the motors and the sprockets. It was painful. And along with that, we had to make sure that everything worked, so that was very difficult. All right, so with the final assembly, Connor made the electronics, very beautiful for that photo. And Steven, had made everything work, and it ended up looking very similar to the electric truck vehicle that's out there.
All right, we just got some stats on the final product here. The shovel can reach speeds of 3.5 miles per hour. It can put an output torque of over 40 foot-pounds, and it can push, which is equivalent to pushing over 80 pounds of snow. The battery life can last for about 25 minutes at full throttle, or closer to 50 minutes for standard use. All right, some successes and failures of the project. This shovel is very capable. It can push a lot of weight, and it's quite easy to use. It's also very quiet, and it does in fact disassemble into 3 parts for storage. Some disadvantages, however, are that it's very heavy and almost impossible to move without the assistance of the motors. Also, it can be a bit unreliable, and it was quite expensive. All right, some improvements we would do if we had more time. We would replace the chain probably with either some sort of belt to increase reliability. Also, we would add a neutral gear so that the shovel can still be moved without the motors. And also, we would work on increasing electronic reliability.
So here's our final cost analysis. We originally planned for about $700 to go into it, but we ended up spending just under $600 in the end. As you can see, the majority of our budget went to actually only 2 items: the gearboxes for our motors, which is what gives it so much power, and the metal. And then the rest of our budget was just comprised of our miscellaneous electronics, hardware, fees, all that boring stuff.
All right, some takeaways here. We learned lots of physical skills, such as Cooper learned how to weld in the shop. I learned a lot of new skills on CADing softwares, and Connor learned how to manage wires in the electronic department. We learned how to work together as a team and use our time well and split up tasks. We also learned how to manage the project, meet deadlines, and get stuff done when we need to get it done. We also learned how to fund the project and make sure that we could get this all built with all the money we had.
So we want to give a couple thanks. 1, thank you to all of you for being here tonight. 2, our good friend and mentor, Ryan Brittingham. 3, Ridgebotics for providing some of the crucial electronic components that we used in our project. 4, the Fossil Ridge High School shop, and Mr. Bevan in particular, for teaching people like Cooper how to weld, as that was a very big part of our project. 5, OtterBox, and specifically Otter Cares. Lucy, thank you so much for being here. We have a gift for you after this, so do stay. And then 6, the greatest thank you of all to Mr. Danahauer for being such an amazing teacher and helping us in every way he possibly can. So if we could get one big round of applause for Mr. Danahauer.
Two things. Number one, I like how Connor said everything he possibly can, which I really didn't help much. These guys killed it. So, and the other thing, I was going to say, I forgot. Never mind. Don't these guys all look really sharp? Isn't it pretty nice to see them all dressed up? So, hey, let's give all the teams a huge round of applause for all that they did. Just a second, we'll turn the house lights up and let you guys go. And I hope everybody came up with a bunch of questions, because now you get to go talk to the teams individually and grill them on all of the important parts of their project. So we're going to go into that gallery walk time. Feel free to help yourself to some more drinks and snacks. And again, I just want to thank everybody for coming tonight and supporting all of the students who worked really hard this semester, and everyone else who's here that supported us as well. So thanks so much for coming, and we'll be all up here, the teams will be up here answering your questions. Thanks.